Okay, let's unpack this. We are barely into January 2026, and the security feeds are already absolutely screaming.
They really are.
It feels less like a new year and more like the frantic pace of the last one simply, spilled over right into our laps.
It never stopped.
We have a sack of sources this week that confirms this relentless pace of vulnerability discovery. And frankly, the sheer breadth of the attack surfaces is staggering.
It truly is. Our mission today is, I think, absolutely critical. We really need to cut through that perpetual noise, the thousands of daily vulnerability reports, and just focus squarely on the highest stakes threats.
Ones that matter right now.
Exactly. We're looking for those vulnerabilities that pose an immediate confirmed risk of RCE, data exposure, or even physical compromise.
And the sources we've compiled, they span everything, from foundational command line tools that every developer uses, to critical enterprise databases, and then some truly bizarre connected physical devices.
Quite a list.
So if we look at the stack strategically, the sources, they seem to reveal three major immediate areas of risk defining the beginning of the year.
I think that's a good way to frame it.
First, we've got these precision supply chain attacks. They're targeting the fundamental tools that we all just trust.
Right, the things we take for granted.
Second, we are dealing with catastrophic data integrity issues in core infrastructure. I'm talking major database platforms.
Yes, and that one is actively being exploited.
And then third, the dangers lurking in the Internet of Things. They're becoming increasingly physical and immediate.
Exactly. We'll be discussing critical arbitrary file writes that could lead to system compromise, massive unauthenticated memory leaks that expose server secrets.
That's scary stuff.
And remote code execution flaws affecting modern platforms, AI libraries, workflow tools. This deep dive is really designed to give you the strategic insight needed to prioritize your patching and defense efforts right now.
All right, let's start at the absolute foundational level, the command line. We're talking about GNU Wget2. Now, this isn't some new, flashy piece of cloud software. This is a workhorse.
It's everywhere.
A command line utility for downloading content from the web, and it's ubiquitous. It's across virtually every Linux and Unix environment. It's the tool everyone just trusts.
And that trust is precisely what makes this flaw, CVE-2025-69194, so strategically dangerous.
Right.
Despite being a high-severity issue with a CVSS score of 8.8, its real-world impact is, I would argue, higher because of its placement in the attack chain.
What do you mean by that?
This is a path traversal vulnerability that allows a remote attacker to overwrite arbitrary files on the victim system. It effectively turns a common trusted utility into a file injector.
So when I think of path traversal, I usually think of, complex web application servers. How does a simple command line downloading tool become the vector for a system compromise like this?
Well, the key is that Wget2 is often relied upon to do more than just fetch a single file. It has more advanced capabilities. And one of which is handling a specific document type called a Metalink document. We probably need to unpack what Metalink is first.
Okay, let's unpack this.
So Metalink is essentially a standardized XML format.
Right.
It's designed to describe download locations. So it often contains multiple mirrors for a file, checksums for integrity verification.
To make sure the file's correct.
Exactly. And crucially, the designated destination file name and path. It was created to make large downloads more robust, more reliable. Wget2 reads this document and then, orchestrates the download process based on what's inside.
Okay, so Wget2 downloads a Metalink file, maybe from a malicious source. It reads the instructions for the download.
Yeah.
And then just blindly executes them.
That's the problem.
Where does that trust break down? Is the flaw in Wget2's implementation, or is it something wrong with the Metalink standard itself?
The flaw is entirely in Wget2's implementation. Specifically, it's a fundamental failure in respecting file system boundaries. The core weakness falls into the category of improper validation of file paths. That's CVE-2025 for anyone keeping score.
Right.
So when Wget2 parses the metadata inside that Metalink document, it fails to sufficiently sanitize or neutralize the file paths specified within the document structure.
And the moment you hear improper validation of file paths, you immediately picture that infamous sequence that breaks containment.
The ... characters.
Precisely. The attacker crafts a malicious Metalink file. Inside, they specify a destination file name that uses path traversal sequences, those characters, to jump backward out of the intended download directory.
So out of the folder you're currently in?
Right. It jumps out of, say, the current working directory and into unauthorized system locations. Wget2 reads this path, assumes the metadata is benign or trustworthy, and is basically tricked into writing the downloaded file far afield.
So it could end up in, what, the etc. directory? Or a user's home folder?
Anywhere the user has write permissions, yes. That is a fundamental security architecture failure. You are relying on a client-side tool to handle metadata with trust, and that metadata is acting as the control plane for file system writes.
100%.
So even though this exploit requires user interaction, a user, or I guess an automated script, has to explicitly tell Wget2 to process that weaponized Metalink document.
Right. There is that step.
The consequences are still immediate system compromise.
Absolutely. And the severity of the file overwrite is limited only by the permissions of the user running Wget2.
Ah, so if it's root.
If the user is root, or if Wget2 is run within an automated process that has elevated privileges, the consequences are, well, they're catastrophic. Think about the potential for arbitrary file overwrite.
Okay, let's run through that. Let's do a scenario. What are the top 3 targets an attacker would hit if they could place a file anywhere?
Well, the ultimate goal, as you suggested, is moving from a simple file write to full code execution.
Getting a shell.
Exactly. So number 1 would probably be overwriting shared libraries. An attacker could replace or modify critical shared libraries, the .so files used by system programs. The next time that system program executes, it loads the attacker's injected code, and boom, local code execution.
Nasty. What's number 2?
Modifying configuration. They could target security configuration files. If an attacker can overwrite or modify files like sudoers configurations, network settings, or even specific cron jobs,
they could give themselves root access.
Or bypass authentication entirely, create new administrative accounts, establish persistent backdoors. It's a keys to the kingdom situation.
And the third?
User environment persistence. Let's say a standard user runs wget2 not root.
Okay.
The attacker then targets their home directory. They could overwrite configuration files like .bashrc or .profile.
Ah, so the next time the user logs in.
The next time they log in or start a new shell, the attacker's command is executed. And that could be anything, but it would likely fetch and run a second stage payload.
It turns an otherwise harmless fetch command into an undetectable system-level file injector.
That's a good way to put it.
And given Wget2's prevalence in automated scripts, CI/CD pipelines, server management tasks, this vulnerability acts as a truly dangerous stepping stone. It's not just a person clicking a link.
No.
It could be an automated system pulling resources from a malicious repository.
That's the strategic takeaway here. The attack surface is shifting toward the core utilities we just take for granted. We trust Wget2 the way we trust tar or grep.
Right. It's just there.
Exactly. And when an obscure feature like Metalink parsing, which, let's be honest, maybe 5% of users ever touch.
Yeah, bad.
When that introduces a path traversal flaw, it highlights the immense complexity and the implicit trust inherent in every single piece of foundational software.
So what's the mitigation reality here? We noted that Red Hat classified this as important, but patches took time.
The reality is sobering. For organizations relying heavily on this tool, patching sometimes requires a full system update or compiling Wget2 from source, which isn't always easy.
Not trivial, no.
So the immediate tactical advice remains difficult to implement perfectly. Avoid processing Metalink files from untrusted sources. But, in today's complex supply chain, defining trusted is half the battle.
That's a great point.
This incident just stresses the need for stringent network-level controls, things like application whitelisting and file system monitoring, to limit the impact of a successful file write until you can get that patch applied.
Speaking of immediate high-stakes risks, here's where it gets really interesting. We're moving from a common command line tool to a massive piece of core digital infrastructure, the MongoDB NoSQL database.
Right.
And this vulnerability, which was rapidly dubbed MongoBleed, has all the hallmarks of a systemic crisis, and for a very good reason.
MongoBleed, or CVE-2025-69194, is exactly that, a systemic crisis. It swiftly moved from discovery to critical status, confirmed by CISA adding it to its known exploited vulnerabilities catalog.
The KV list.
The KV catalog, yes. And when CISA adds a vulnerability to the KEV list, it signifies that attacks are not theoretical.
No, it means they're happening.
No. They are confirmed, active, and impacting production environments globally.
The nickname Mongo Bleed immediately triggers memories of Heartbleed from, what, a decade ago?
It does.
And if the mechanism is similar, involving a leak of server memory, that suggests a worst-case scenario for data exposure. What's the actual scope of this flaw?
The scope is massive, which really added to the panic. It affected MongoDB server versions spanning nearly a decade.
A decade?
Yes. From the older 3.6 branch all the way up through the latest 8.2.2.
Wow.
That means organizations that thought they were keeping up with maintenance but maybe weren't on the absolute latest patch branch were still critically exposed.
So walk us through the technical flaw. What causes this bleed?
The technical flaw is a memory leak, and it's caused by an issue in how MongoDB handles compression, specifically zlib compressed protocol headers.
Okay.
It's an error due to mismatched length fields within those headers when processing BSON documents.
All right, let's break that down slightly. For anyone listening who hasn't dealt with database protocols, a BSON document is... It's essentially binary JSON, right?
Correct. It's the format MongoDB uses to store and transmit data efficiently.
Got it.
So when a BSON document is compressed using zlib for faster transmission, the header should accurately state the length of the compressed data and, crucially, the length of the expected data after decompression.
That makes sense.
The vulnerability arises because an attacker can craft a document where they intentionally inflate the expected document length field in the header.
Mismatched fields. So the server thinks it's dealing with a huge amount of data and reserves memory for it, but the actual compressed payload is much smaller, is that it?
Precisely. The decompression logic runs, it processes the small payload, but because the length field was deliberately inflated, the server then attempts to read data from the memory location immediately following the compressed document.
And that memory is what?
That memory, which the server assumes is the legitimate continuation of the document, is actually uninitialized heap memory. It's the residue of whatever the server was just doing.
That's the critical point.
I
Uninitialized heap memory. So it's essentially digital garbage, but one person's garbage is an attacker's goldmine.
Exactly.
And this exploit doesn't require authentication.
That is the single most critical aspect. This is an unauthenticated vulnerability.
Wow.
An attacker requires no login, no prior access, and no complex exploit chain. They only need to establish a simple TCP connection to the exposed MongoDB instance and send this specially crafted BSON document.
And the server just leaks.
The server leaks the heap memory contents immediately upon receiving the request.
That sounds devastating. If an attacker can just sample the server's memory space, what kind of critical operational secrets are they harvesting? Can't just be random bytes.
No, it's not random at all. When a server processes sensitive information, that information sits in memory, sometimes briefly, sometimes for longer. The fragments exposed by MongoBleed can contain highly sensitive operational and credential data. Our sources indicate attackers could potentially harvest, well, a few key things.
Like what?
First, authentication credentials. In-memory fragments of internal credentials or keys used for inter-server communication, client authentication, or replication.
Okay, that's bad.
Second, encryption keys. Keys used for encrypting internal MongoDB logs or even data if TDE transparent data encryption keys are briefly cached in that memory space.
Even worse.
And third, this is a key technical detail, wired tiger parameters.
Wired tiger, that's the storage engine MongoDB uses, right?
It is. These parameters essentially control the storage engine's entire behavior, its efficiency, its caching, its structure. Leaking them provides massive insight into the database's internal layout and configuration, which would really aid future attacks.
And there's more, I'd imagine.
Oh, yeah. Things like internal paths and context, Docker paths, file system locations, internal MongoDB logs, and connection metadata like client IP addresses and connection UUIDs.
So if I were an attacker, having those wired tiger parameters and internal paths, that gives me a blueprint for how to interact with the database.
It's a roadmap.
It tells you how to navigate and target files on disk. This moves the attack from just a random data leak to a highly targeted reconnaissance tool.
Precisely. It allows the attacker to connect the dots and move laterally or, deepen their compromise. And this wasn't a niche problem. The real-world exposure footprint for MongoBleed was terrifying.
I recall the security scan reports being absolutely frantic when this dropped.
They were. Security researchers using tools like Shodan and sanitise rapidly identified somewhere between 75,000 and 100,000 potentially vulnerable MongoDB instances.
100,000?
Potentially, yes. And they were exposed directly to the public internet.
Oh, that's the killer.
This exposure, combined with the unauthenticated nature of the memory leak, created a global emergency. The reports indicated top exploited geographical locations included the US, China, and the EU, basically, wherever MongoDB is commonly deployed for modern web services.
I can only imagine the holiday season that followed the public release of the exploit. I think it was around Christmas, right?
There was.
Managing a zero-day during a typical week is difficult. Dealing with 75,000 exposed critical databases during the holidays sounds like pure operational misery.
It was a nightmare scenario for thousands of DBAs globally. And this brings us back to strategic defense. If you were managing any of those exposed databases, patching was the only true solution. But in a large, sharded environment, that takes time.
So what was the urgent remediation path if you couldn't patch immediately?
Well, the primary advice was an immediate upgrade to patched versions, 4.4.30, 5.0.32, and so on.
Right.
However, if immediate patching was delayed, there were two critical alternative workarounds that needed to be deployed instantly. And they serve as a great reminder of security fundamentals.
Okay, what were they?
First, disable zlib compression. Since the zlib compression protocol headers were the core vector for the mismatch length fields, just disabling zlib compression eliminated the attack path entirely.
But there's a performance hit.
There's a performance penalty, yes, but it stopped the bleed immediately.
In a second.
Network isolation. This is the harsh lesson. Database servers should never be exposed directly to the public internet.
Ever.
They must be isolated, accessible only via trusted internal networks, VPNs, or highly segmented cloud environments. 75,000 exposed databases is not a technical failure of MongoDB. It's a monumental architectural failure by the organizations deploying them.
That isolation principle is the ultimate strategic takeaway, isn't it? If the database wasn't reachable by an unauthenticated client in the first place, this critical vulnerability becomes a non-issue.
A complete non-issue.
It's a classic example of defense in depth failing at the outermost, most crucial layer. Okay, then we shift gears again. We've covered low-level tools like Wget2 and core infrastructure like MongoDB.
Right.
Let's pivot to platform-specific vulnerabilities that target modern applications, specifically those governing email, automated workflows, and the rapidly expanding AI ecosystem. We are moving up the application stack, but the consequences remain the same. Remote code execution, often with perfect criticality scores.
And what's fascinating here is that the attack vector fundamentally shifts.
How so?
We move from, technical flaws and low-level parsing buffer overflows or zlib bugs to flaws in logic, specifically flaws in trusting complex application routines like expression engines and serialization functions.
So the attack target is no longer the C code, but the Python or C# logic flow itself.
Exactly.
Speaking of internet-exposed servers, that isolation problem we just talked about isn't limited to databases. We're seeing catastrophic RCE flaws appearing in ubiquitous applications that, by their nature, have to be on the edge of the network.
That brings us to Smarter Mail, a commercial mail server platform. This vulnerability, CVE-2025-691, clocked in a perfect CVSS 10.0 critical rating.
The 10.0.
In the world of security, a 10.0 is the signal fire. It means exploitation is almost trivial, unauthenticated, and grants complete control.
What made this flaw a perfect 10.0?
The severity stems from two factors: the nature of the flaw and the nature of the target. The flaw itself is an unauthenticated remote code execution, achieved through arbitrary file upload. The vulnerability allows an attacker, without ever logging into the system, to upload any file to any location on the mail server's file system.
Wait. Any location?
Yes, any location. There was a critical failure in the handling of file path inputs during an upload process that was exposed to the public internet.
And mail servers, by definition, have to be accessible globally to send and receive email.
That's the target part of the equation. The source material described the exploit path as trivial.
Trivial, huh?
Because once the arbitrary upload is achieved, the attacker simply uploads a malicious file, likely a web shell, a small script that lets them run OS commands to a publicly accessible directory, like a webroot folder.
And then they just browse to it.
Once uploaded, they browse to the file's URL and the code executes. And just like that, they have full control over the email server.
And since that server handles all email traffic, potentially houses archived messages, and connects to internal networks, that's a massive beachhead into the organization.
A huge one.
So immediate patching must be mandatory, but what if patching wasn't immediate?
Immediate patching was the only true defense upgrading to build 94.430 higher. But given the ease of exploitation, security teams have to be deeply paranoid. Beyond patching, the critical step is post-patch forensics.
So what are they looking for?
They need to hunt for indicators of compromise that occurred before the patch. Specifically, organizations must look for unusual or unexpected files,
Like web shells.
particularly executable scripts or files in web root directories that appeared on the mail server's file system in the days or weeks leading up to the patch. The presence of a file like that is a definitive indicator of a successful upload and, potential ongoing backdoor access.
That brings us from external-facing email to internal-facing automation.
Right.
We pivot now to N18, the open-source workflow automation platform, which also suffered a near-perfect RCE flaw, CVE-2025-68693, rated at CVSS 9.9.
The N8N vulnerability is a classic and a very worrying illustration of a modern application architecture mistake.
And what's that?
Confusing user input with executable instructions. The remote code execution occurs within its core function, the workflow expression evaluation system.
Okay, so N8N is designed to automate complex tasks, often connecting different services. And users, authenticated users, in this case, they write logic, often in JavaScript-like expressions, to define how data moves and how workflows should execute.
Exactly. The platform relies on evaluating these user-supplied expressions dynamically. The fatal flaw was that expressions supplied by authenticated users during workflow configuration were being evaluated without sufficient isolation from the underlying Node.js runtime environment.
No sandboxing.
Exactly. That lack of sandboxing allows an attacker to break out of the expression environment and execute arbitrary operating system commands. This is known generally as expression injection.
Okay, but since this requires an authenticated user, does that lower the risk significantly compared to a perfect 10.0 like Smarter Mail?
Strategically, it shifts the threat model.
How so?
It reduces the risk from anonymous internet scanners, sure, but it drastically increases the risk from insiders, or, more commonly, from successful phishing or credential theft that targets an employee with access to the platform.
Right.
In an enterprise setting, the consequences are enormous.
Why are the consequences so severe? I mean, it's just workflow logic, right?
If we connect this to the bigger picture of organizational data flow, an automation platform like N8N is the central nervous system.
Okay, I see where this is going.
Exploiting this RCE grants the attacker potential control over manipulated data, as the system often holds credentials for other services' databases, APIs, cloud accounts.
They can pivot.
They could modify or delete automations to disrupt business processes or, crucially, gain complete server control, particularly if the N8N instance is self-hosted and exposed to the internet or shared among multiple users. An attacker could pivot from controlling the workflow logic to controlling the underlying server and all its secrets.
That makes the 9.9 rating well-deserved. The context of the application being this key hub for data movement elevates the severity of what is otherwise a standard RCE flaw. This brings us to the newest and fastest-growing attack surface, the entire AI ecosystem. We are seeing critical RCE flaws affecting libraries responsible for model serialization and workflow orchestration, specifically LangChain and Hugging Face. Let's start with LangChain and the Lagrange vulnerability, CVE-2025-68694.
LangChain is fundamental. It's the framework that allows developers to build complex LLM applications and agents, chaining together different data sources and models. This critical serialization injection flaw, CVSS 9.3, exposes a deep architectural risk inherent in modern AI development.
Which is?
The process of turning objects into data and back again.
Okay, so let's clearly define serialization. It's the process of taking a live software object like an agent configuration, a message, a memory buffer, and turning it into a stable data format like JSON or YAML so it can be stored or transmitted.
Right. And deserialization is the reverse process.
So where did LangChain fail in this fundamental concept?
The failure was rooted in a lack of proper distinction between benign user data and internal executable object definitions.
Okay.
LangChain uses a specific internal marker key, LC, within dictionaries to flag structures that should be interpreted as legitimate LangChain objects during serialization.
So that LC key is essentially the magic marker that tells the system, hey, this isn't just data, this is a defined configuration object.
Correct. And the vulnerability arose because the core functions, dumps and dumped, responsible for this process, failed to properly escape or neutralize free-form dictionaries supplied by users. If those dictionaries happen to contain that internal marker key, LC.
I see the attack now. The attacker crafts input data, maybe a user prompt or a configuration setting, that looks innocuous, but happens to contain a dictionary structure with that magic
Yeah.
LC key. And that tells the deserializer, treat me as an object.
Precisely. When that user-controlled data is later deserialized by the application, the system trusts the LC key and treats the user input as a legitimate internal LangChain object structure rather than inert user data.
And that lets them inject things.
It allows the attacker to inject arbitrary object definitions. The consequences detailed in the advisory are severe. Extraction of sensitive environment variables, API keys, database connection strings, credentials for remote services,
Everything.
and the potential for full remote code execution if the attacker can successfully construct a malicious object that runs code upon instantiation.
It's a classic injection scenario, just disguised within the complexities of an AI application. The fix required updating LangChain core, I assume.
It did.
And I imagine the strategic advice was to treat all data, especially data coming from or through an LLM, as inherently untrusted.
Absolutely. We have to assume that LLMs, being text predictors, can be manipulated or jailbroken to generate malicious output that contains these structures.
And this pattern-confusing data with code is sadly echoed across the wider AI model supply chain, which brings us to Hugging Face.
It does.
Hugging Face is the central repository for almost all open-source AI models. We saw multiple high-severity RCE flaws here, like CVE-2025-69194, a critical 10.0 in components like small agents. What's the common thread in these RCEs?
The common thread is deserialization of untrusted data and code injection during model processing.
Okay.
The single biggest culprit here is the reliance on the Python pickle format for model weights and checkpoints.
And pickle has been known for years to be inherently unsafe, right?
Yeah.
If you deserialize a malicious Python pickle file, it can execute arbitrary code.
It is notoriously unsafe. The problem is that it is often the most convenient way to serialize complex Python objects, including machine learning models.
So convenience wins over security.
Often, we saw high-severity RCE flaws affecting core components like accelerate and transformers because they were processing untrusted model files, sometimes from community uploads, that contain malicious pickle payloads.
But it wasn't just pickle. There were RCEs linked to model conversion, weren't there?
Yes, and this is where the supply chain risk really deepens. There were code injection RCEs, CVSS 7.8, specifically linked to checkpoint conversion routines in model architectures like SOD and Hubert.
So when you're converting a model from one format to another.
Right. The conversion routine itself can be tricked into executing code embedded in the model file. The implication is profound. Processing or loading an untrusted AI model file, even just analyzing it, can lead directly to remote code execution on your model-serving server or development environment.
This essentially confirms that in the AI ecosystem, the model itself is the new binary.
It is.
It's the potential executable payload. It's no longer just a data file. It's a potential bomb waiting to go off upon deserialization. That brings us to our final major theme, which is arguably the most pervasive and sometimes the most physically threatening. The exposure of ubiquitous, often unmonitored devices that form the bedrock of our personal and physical infrastructure. We are talking about routers, cameras, and, as we'll discuss, even mobility aids.
Right.
This confirms that physical location and device simplicity do not guarantee security. In fact, they often guarantee poor security by design.
The pattern we see across the networking hardware sector is a persistent, depressing failure in fundamental input handling.
What do you mean?
I mean, we're discussing buffer overflows and command injection flaws, vulnerability classes that software developers should have mastered and eliminated 20 years ago.
But they're still here.
Yet, they recur across almost every major vendor's consumer and small office hardware.
Let's look at Tenda, for example, which presented an incredible cluster of high-severity flaws this period. We're seeing multiple buffer overflows rated 8.8 and critical command injection issues rated 9.8 across many of their popular consumer models.
Yes. Tenda models like the AC10U, AC23, and WH450 were just deeply affected. And when we dig into the specifics, we see a pattern. The flaws reside in the web interface functions designed to handle user configuration via POST requests.
The admin panel.
Right. For instance, the buffer overflows were typically found in functions responsible for setting network parameters, like from mabset lanup in the AC10U or formset PPTP user list in the AC23.
So these functions take user-supplied strings, say a network mask or a list of VPN users, and use an unsafe function, like Stracopy, which doesn't check the size of the destination buffer. Is that it?
That's exactly it. The attacker sends a request with an overly long value in an argument like landmask or a specific list item, and it causes the memory buffer to overflow.
And that leads to RCE.
It can corrupt adjacent memory structures, which an attacker can then hijack to redirect program execution and achieve RCE. And the command injection issues follow a similar path, but they often skip the memory corruption step entirely.
Command injection means the input data is being executed directly as an operating system command, right?
Correct. Take the Tenda WH450, for example. We saw a critical command injection where manipulating the IP address argument in the network diagnostic tool endpoint allowed the attacker to inject arbitrary shell commands.
And the router just runs them.
The router executes these commands immediately, granting the attacker control. And here's the scary part. The sources confirm that exploits for many of these Tenda issues are publicly disclosed, often within days of the CVE being published.
So the defense window is basically non-existent.
It's gone.
And Tenda is not an isolated case.
Yeah.
We saw the same consistency across D-Link, Linksys, and specialized industrial hardware like JD Cloud.
It's the same common failure, poor input validation. D-Link's DWR M920 router had multiple 8.8 high buffer overflows and 6.3 medium command injections via firmware upgrade functions.
A firmware upgrade function.
Yes, a function designed to talk to the modem component. If you can inject commands into a firmware upgrade routine, you gain powerful control.
Wow.
Lynx's E5600 routers also suffered a critical 9.8 command injection via the mc.ip parameter in the runtime.mcclone function. Again, exploitation via basic configuration endpoints.
That pattern of configuration endpoints being the RCE vector is just so consistent. Attackers know these endpoints are complex, often handle strings without proper bounds checks, and are exposed via the web interface.
And if we look at industrial exposure, JD Cloud NAS routers had an unauthorized remote command execution vulnerability, CVSS 9.8. This highlights that any device designed for slightly more advanced networking operations, where dynamic DNS or other specific services are involved, often harbors critical, easy-to-exploit flaws if left exposed. This isn't about complex attack paths.
No, it's about checking the length of a string before copying it.
It's that simple.
Now we get to the vulnerability that is, quite frankly, the most shocking, because it introduces a direct physical threat vector to a user's body and mobility.
This one is something else.
We're talking about the Will Model C2 and Model F power chairs and CVE-2025-69194.
This vulnerability scored a critical CVSS 9.8, and the description should send chills down the spine of any safety engineer.
What is it?
The devices do not enforce authentication for Bluetooth connections. Full stop. There is no security pairing mechanism built into the communications protocol.
No authentication. So anyone within Bluetooth range, which could be 30 feet in a crowded public space, a hospital, an airport, can just connect to this critical mobility device.
Exactly. An attacker within Bluetooth range can pair with the power chair and immediately issue unauthorized movement commands.
They can drive it.
They can override crucial speed restrictions, manipulate acceleration profiles, and alter configuration settings, all without needing any credentials, PIN, or any form of user interaction.
The implication here is enormous. It's not just a data breach. It's the ability to physically and remotely manipulate a device someone is relying on for their mobility and physical safety.
Right.
Imagine being in traffic or on a ramp and having your controls hijacked.
That is the core strategic point. For too long, the security community has treated IoT flaws as either data risks or denial of service risks. This flaw introduces immediate, undeniable physical safety risk into the cyber threat model.
It's a wake-up call.
It's an urgent call for manufacturers of all connected physical devices, medical, mobility, industrial, to integrate authentication as a fundamental, non-negotiable security requirement. This failure to enforce credentials means the core design philosophy was security by obscurity.
Just assuming no one would look at the Bluetooth protocol.
Right.
Firmware updates were rushed out, I presume, but the inherent flaw exposes a deep lack of security by design from the ground up.
Yeah.
You can't just retrofit trust easily.
You absolutely cannot. And the lesson is, if a device has a radio and it moves, it needs physical access controls.
And finally, we need to address the exposure of older and operational technology systems.
Yes.
The fact that a vulnerability is old doesn't mean it's irrelevant. It means it's had years to mature and likely sits unpatched in critical environments. We saw several older flaws recently published as CVEs, reinforcing that these devices are prime targets because they are often forgotten.
Like the FLIR thermal traffic cameras, those devices have been running for years, yet we are still seeing critical CVEs published now.
Right.
Yes, the FLIR AX8 thermal cameras, often used for public infrastructure and traffic monitoring. CVE 2018-25138 addressed the presence of hard-coded SSH and web panel credentials.
That could not be changed by the user.
Exactly. An attacker could gain unauthorized shell access and web login using predefined, non-configurable usernames and passwords.
Hard-coded credentials are the definition of low-hanging fruit. It means every single camera deployed uses the exact same master key.
The exact same one. And to compound the issue, related flaws allowed unauthenticated access to the live video streams via standard endpoints. These cameras, designed to monitor traffic flows, were effectively broadcasting their live feeds and login portals to anyone who knew the default master key and the common access path.
That's just,
Yeah.
wow. It reveals massive operational data and security weaknesses in civil infrastructure.
It really does.
And we also saw issues pop up in specialized industrial and remote communications gear, which are often used in critical OT systems.
That brings us to the Comtech Advanced Satellite Modems. CVE 2025-69015 detailed an incorrect access control flaw. An attacker could change the administrator password and escalate privileges merely by sending a crafted POST request.
So it's not a complex RCE.
No, it's a simple failure to validate whether the user making the request has permission to change the top-level admin password.
It's just a forgotten access control list on a basic web form.
A simple error with huge implications. These modems are frequently deployed in remote operational technology systems, think SCADA environments, remote energy monitoring, satellite comms centers. Gaining control over the satellite modem gives an attacker control over the physical data link for a remote, critical site.
And finally, let's quickly revisit the aging home and small office networking equipment, because the exploitation method here is frighteningly simple.
It is. We saw high-severity privilege escalation flaws in older ZBL and Newcom routers. The mechanism for compromise was simple configuration file disclosure. Low-privileged users could access configuration backup endpoints via crafted HTTP/GT requests.
So if I know the URL path for the configuration backup file, the router just hands it over.
Often, yes. In the Newcom case, this request would retrieve the configuration backup file. And these files almost universally contain the stored admin password, often merely base 64 encoded.
So you grab the file, decode the password.
And you instantly gain superuser access. It is a recurring, easily preventable theme that guarantees total compromise in unpatched legacy IoT devices.
It's the equivalent of leaving the master key under the doormat and just encoding the combination in pencil.
Precisely. And this is why these older vulnerabilities remain active threats. The path to full privilege escalation is often ridiculously easy.
We've covered a massive amount of ground here, from Wget2 on a central server to the Bluetooth module on a smart wheelchair. Let's try to synthesize these points to highlight the major strategic themes emerging from this rapid burst of critical vulnerability disclosures.
Okay, if we look at the stack, we saw 3 undeniable thematic risks that should inform every security strategy moving forward.
What's the first one?
1. Precision supply chain attacks. Demonstrated by Wget2, where a vulnerability in a trusted foundational utility allows high-impact file overwrites using obscure features. The attack is hidden in the benign.
Okay, number 2.
2. Immediate widespread data breach risks, epitomized by MongoBleed, which leveraged a low-level protocol bug to leak internal server memory from tens of thousands of exposed databases. This was a classic bleeding vulnerability with global scale.
And the third theme?
The growing, diverse attack surface. The sheer variety of exposed, vulnerable devices in our environment, from critical AI platforms to motorized wheelchairs to routers, shows that if it runs code, it's a target, regardless of its function or its age.
So what does this all mean for the people managing and defending these systems? What are the common recurring failure patterns that allowed these attacks to gain such high severity ratings?
This raises a really important question about fundamental software engineering practices, especially around handling input and execution context. We can identify 3 high-impact vulnerability classes recurring across all these layers.
Okay, lay them out for us.
First, path traversal input neutralization failure. This is the core Wget2 failure. User input is mistakenly interpreted as navigational commands, allowing access to unauthorized file paths. It's a failure to constrain external data. Second, serialization injection context confusion. This is the AI threat we saw in LangChain and Hugging Face. It's the failure to distinguish between inert user data and executable object structures. When data is treated as code, the system is compromised. This is really the new frontier of injection attacks.
And the third pattern?
Blatant lack of authentication and bounds checks. This is the core IoT problem. The router flaws were primarily buffer overflows, a failure to check input length or simple command injection, and the Wilhelm wheelchair flaw and the Comtech modem flaw. They demonstrate a fundamental lack of authorization enforcement, a failure to ask, are you who you say you are, and are you allowed to do this?
It's a comprehensive failure across all layers. But the ultimate takeaway, the pattern we see confirmed by the source material, is the pace of exploitation.
Yes.
When a vulnerability is disclosed, the race is no longer measured in weeks or days, but in hours.
That's absolutely correct. We saw immediate public release of working exploit code for critical flaws like Mongo Bleed, the Smarter Mail RCE, and multiple Tenda and D-Link issues. The gap between a vendor announcing a patch and attackers weaponizing the vulnerability has effectively collapsed to zero.
So what does this mean for strategic planning? How do you defend in a world where that gap is zero?
Given that exploits for critical flaws are being publicly released almost immediately, the effective window between disclosure and exploitation is gone. Traditional security strategies that rely on slow, measured patch cycles or on the hope that attackers won't immediately weaponize the information, they're obsolete.
So what's the provocative thought for everyone to take away?
The challenge you need to be mulling over right now is this. How must security strategy change when time itself is no longer a reliable defense buffer? You have to move toward proactive strategies, like disabling exposed features, like zlib compression or default admin functions, or applying isolation, like no public exposure for databases before the patch is even available. Because relying on the availability of the patch itself is proving to be far too slow. You must assume compromise and enforce isolation at the network edge immediately.